warahmatullahi wabarakatuh. Bertemu kembali. So we will continue our lesson on simple harmonic motion. Okay. Today we are going to learn about energy in simple harmonic motion. So we will concentrate on string. Okay. Not string, spring. To explain about energy in simple harmonic motion. Okay. First of all, you should know what is the total mechanical energy in simple harmonic motion. In simple harmonic motion, the total mechanical energy is ET, the symbol for total mechanical energy, and then is equal to kinetic energy plus elastic potential energy. These two types of energy is called mechanical energy. So now we expand the equation here. Kinetic energy is equal to half mv square, okay, and then plus elastic potential energy. This is elastic potential energy, not gravitational potential energy. Remember, there are two types of potential energy. One is gravitational potential energy and another one is elastic potential energy. For this example, we will use elastic potential energy because the spring is about elasticity, okay, not about the gravity or height. Okay, so now we will use elastic potential energy. The equation for the elastic potential energy is half kx square. Okay, so this is the example, the equation for total mechanical energy in simple harmonic motion. Okay, you have to remember this one. So again, total mechanical energy is the sum of kinetic energy and elastic potential energy. Okay, we go to the explanation here. Okay, actually this is A, B, C and D is the same spring. Okay, the difference is the position of the load that attached to the spring. Okay, the first one, A, look at the first one. The first one, I want you to imagine, okay, there's a spring that is placed horizontally, and then someone pull it to the right, and then release it. So it will move back and forth, and continuously. Okay. So look at this part. Okay. Look at this spring and look at the position of this load. Okay, this load, the position is at minus A. Okay, which is this is the extreme point. Okay, at this side, for this side, it will move back and forth. So this is the direction of when it moves back. This is forth. So here is it will displace at the maximum point, which is called this is from the length from x equal to 0 to x is equal to minus A is the amplitude. So this is the extreme point, or we call it extreme point. Okay. An extreme point means at x is equal to minus A. Okay. The object here will stop momentarily. Okay, as it changes the direction. Okay. So here at this point it will stop for a moment. That means at this point V is equal to 0. Okay, so at this point V is equal to 0 because it will stop momentarily as it changes the direction. Okay, at this point, okay, when the mass or load at this point, what is the total mechanical energy for this condition? Okay, So at this point, the total mechanical energy is equal to half mv square, okay, plus half ka square. Okay, so here v, for this position, v is equal to 0 here. So the total mechanical energy is equal to half ka square. This is when the position of the object is at the extreme point. Okay, this is for A, the explanation for A. And then the explanation for B. Look at the position of the object. The position of the object is at equilibrium condition. It is at equilibrium point. X is equal to 0 when the system is x is equal to 0. Here is when x is equal to when x is equal to the maximum displacement, or we call it the amplitude, or we call it the extreme point. Okay, for B, the load here, okay, pass through this position, through this equilibrium point. At the equilibrium point here, okay, the value of V here is maximum. Alright, the value of A is maximum. At x is equal to 0, the value of V is maximum. That means at this point, this is the highest velocity. Okay, amongst these 3 points, this is the highest velocity. So here we call it maximum velocity. The velocity here is maximum. Okay, so what is the total energy at this point? Total energy at this point is EP. Okay, similar, we use this equation, is equal to half mv square plus half kx square. Oh, sorry, this one is not A, this is x. Okay, back to this explanation. X here is equal to A. X here, this is x is equal to A, this is x is equal to plus A. So you substitute with this x with minus A. So you will get here total energy at that position is equal to half Ka square. Okay, for this position, when the object is at equilibrium point, the total energy is equal to, here is half m v, this is v here is the maximum. So we write v maximum square. Okay, and then here, what about the value of x here? The value of x here is equal to 0 because it is at the equilibrium point. So here you substitute 0, it becomes 0. So the total energy at the equilibrium point is equal to half mv squared, where v here is the maximum velocity. Okay. What about the total energy at this point? This is the extreme point. Same with this case. Same with this case. Okay, it is at the equilibrium. At the maximum point, but at the maximum displacement. So the total energy here becomes half mv square plus half kx square. So here, when the object reach at this point, it will stop momentarily as it changes the position, the direction. So here, it will stop for a moment. So V here becomes 0. So the total energy is equal to half k x here you replace with a. So it becomes half ka square. So it's similar with a. Okay, this one. Because this is at the extreme point, and this is also at the extreme point. or is at the displacement where x is equal to the value of amplitude. Okay, have a look at D. For D, the object is not at equilibrium position, and the object also is not at the maximum displacement, but it is at the intermediate between x is equal to 0 and x is equal to plus a. Somewhere here. It's somewhere here. It's somewhere here. So how you are going to calculate the total energy? So total energy is equal to half mv square plus half kx square. So at this point, okay, at this point, the energy is from kinetic energy. Part is the energy. The part of energy is kinetic energy, and another part is elastic potential energy. That means there's a value of V and there's a value of X here. So the total energy will be both here, both the summation of kinetic energy and elastic potential energy. Okay, so this explanation is how you are going to find the total energy at a given position. For example, at an equilibrium position, or at the maximum displacement, or at any arbitrary position here. Okay. From here, we know that you can calculate the maximum energy by using two equations here. One is this one. Okay, one is this one. Or you can calculate by using this equation. One is you can calculate by using total energy is equal to half Ka square, or you can calculate the total energy by using Et is equal to half mv maximum square. Two equation here. This is total energy. This is also total energy. Both can be used. It depends on the question. Alright. So we come back to this equation. The total mechanical energy is the sum of kinetic energy plus potential energy. Okay. So from here, total energy. Total energy here, you can use this one or this one. Okay. Choose one. For example, here I choose this one. Total energy. So total energy here, I substitute this total energy with half Ka squared. So the equation becomes half Ka squared is equal to half mv squared plus half Kx squared. So from here, factorize half. Okay, you factorize half, factorize half, so it can cancel each other, this side and this side. So the equation becomes Ka is equal to mv squared plus Kx. Okay, so I bring K at one side. So Ka square minus Kx is equal to mv square. Okay, so here K, factorize K, it becomes A square minus X square is equal to mv square. Okay, so K divided by M is equal to sorry, at this point So now I want to make V as a subject. Okay, V as a subject. So V here, V square is equal to V as a subject. So V is equal to K divided by M, and then here is A square minus X square. Okay, so this side, look at here, this is V square. Okay, so I continue here. Alright, so V is equal to sub K over M, and then A square minus X square. So remember, sub K over M. Before this, you learn in spring systems, sub K over M is equal to omega. Remember this one? Okay. So here, if K over M, so here is sub K over M is equal to omega. You replace this one with omega, and then square root A square minus X square. So this is V. Alright. This is one way how you're going to find the value of velocity in simple harmonic motion. Before this, to find the velocity, okay, you have to differentiate the equation. That means from the displacement to the velocity, you differentiate the displacement equation, you can get the velocity. Or another method that can be used to find the velocity is by using this equation. V is equal to omega sub A square minus X square. So this one can be used if you know the value of A and if you know the value of the displacement. Just substitute inside this equation, you can get the velocity. Alright, so this one, you don't have to derive like this. This is, I just want to show you how to get this equation. This equation is from the total mechanical energy. Okay, so finish about total mechanical energy. Okay, see you again after this. Okay, bye. Assalamualaikum. Example 7.4, page 138. A spring of unknown springs constant is attached with a weight of mass 0.2 kg. When it is released from rest, the spring extends to a distance of 5 cm before it stops. The weight is then pulled down 10 cm further downward and then released. If the system oscillates with simple harmonic motion, compute the spring constant and angular frequency of the system. Okay, this is the figure. Look at the figure here. Okay, this is when there is no mass at the end of the spring. Okay, so when you attach a load, which mass of the load is 20 kg, 0.20 kg. The spring extend 5 cm. Okay, so 5 cm is here. Okay, this is the end of the spring. The end of the spring is extend 5 cm. Okay, the weight is then pulled down 10 cm further downward and then release. Okay, and then the third situation, the spring is then pulled, pulled down, downward pull is then pulled down 10 cm further. So, for example, this position. So from here to here is 10 cm. This is the situation of the spring. Compute the spring constant and angular frequency of the system. This is when the system is in equilibrium, this part, this one. Okay, when the system is in equilibrium. This is the spring when there is no load attached at the end of the spring. Okay, so look at this part. Okay, look at this part. This is mg. Okay, this is kl. Remember this one? Okay, this one. Okay, this figure. Look at this figure. This is mg. Okay, mg, and this is kl. Okay. Alright. So here, back to the question. Okay, back to the question. Compute the spring constant and angular frequency of the system. So from here, if you want to calculate the spring constant, okay, so look at this part. Look at this part. Mg, okay. If the system is in equilibrium, that means the net force is equal to 0. Net force in y direction. There is no x direction. So here, based on this figure, okay, number 2, figure number 2, this is number 1, number 2, number 3. Okay, based on number 2, okay, KL is positive, minus mg is equal to 0. So here, KL is equal to mg. So from here, you can calculate the spring constant. K is equal to mg divided by L. So here, m is 0.20 and then 9.81 divided by L. Divided by L, here is 5 cm. Okay, so 5 cm, that means 0. Divided by 0.05. Okay, so when you calculate, you will get K is equal to 39.24 Newton per meter. Okay, that is about the spring constant. And then how you are going to finish about spring constant. And then now we are going to calculate the angular frequency. So remember, angular frequency, angular frequency, okay, angular frequency omega is equal to sed k over m. Remember, you cannot use omega is equal to 2 pi f because we don't know the value of f. So we use sed k over m. Okay, is equal to k is 39.24 divided by 0.2. Okay, so when you calculate here, you will get 13.96 radian per second. Okay. B, compute the total energy of the system. So total energy, remember total energy, E is equal to half Ka square. Okay, so here the maximum displacement. Okay, look at here. Look at this part. Look at this part. From here, from the end of the spring here to this spring. Okay, from the end of the spring. Oh, not. Okay, so the label here is wrong. Sorry. You can see here. So look at this part. From here to here. This is 10 cm. That means this is the maximum displacement. When someone pull this object, okay, someone pull the object, okay, pull from this point to this point, okay, so the person pull 10 cm and then release it. That means the 10 cm here is the amplitude. Okay, so here if you want to calculate the total energy is equal to half Ka. K is 39.24 and then A here is 0.1. Okay, 0.1 square. Okay, when you calculate, you will get the energy. The total energy is 0.2 joule. Okay, compute the net force acting on the weight at x is equal to 5 cm below the equilibrium position. So compute the net force. Okay, if you want to calculate the net force, remember Hooke's law. We use the Hooke's law equation. Okay, F is equal to minus kx. Okay, so here just put the value 39.24 times x. Here is 0. Okay, 0. Okay, XCM below the equilibrium position. So this is the equilibrium position. Okay, for example, this is the equilibrium position. Okay, this will be the equilibrium position, and then the net force acting on the weight at XCM below. So XCM below means below this point. Below this point. So the direction of the displacement is downward direction. So here we have to put the value of x here is, okay, x here is minus 0 0.05. 0.05. F is equal to kx. Okay, 0.05. So here you will get, okay, never mind, if you don't want to put this sign, it's also okay. So 39, try to calculate, 39.24 times 0.5. F is equal to kx, 1.96 minus, okay, minus 1.96 Newton. This is the net force. Okay, the net force acting on the weight at x is equal to 0.05 meter. Okay, and then we go to question D. Okay, question D. Okay, question D. Compute the velocity and acceleration of the system at x is equal to 5 cm below the equilibrium position. So for this one, okay, so V, remember V is equal to omega z a square over x square. So we will use this equation, okay, to find V. Omega here is equal to 13.96 square. Then A is equal to 0.1, which is 10 cm square, minus 0.05 square. So here you will get the velocity here. Okay, try to calculate the velocity. When you calculate, you will get 1.21 meter per second. Okay, this is the way how you're going to calculate the velocity at a certain point. Okay, so A is equal to minus omega square x. Remember this equation? Don't forget this equation. Okay, so this one, omega square, and then x. X here is, okay, it's, okay, it is optional here. You can put the negative sign, or if you don't want to put the negative sign, it's also okay. So I will explain to you why. Okay, 0.05. Okay, so here minus omega is 13.96 square times 0.05. Okay, so here it is equal to minus 9.74 meter per second square. So what is meant by the negative sign here? Question D and also question C here, the negative sign. The negative sign means that the direction of acceleration and the direction of force, okay, both A and F, the direction of force and the direction of acceleration, both quantity is always opposite the direction of the displacement. That means, okay, for example here the spring, and then the object. Okay, someone pull. Okay, someone pull. Okay, for example, from here to here, for example, here is 5 cm. When someone pull the object until this position, okay, not someone pull, when the object move from this position to this position, and then and then the total displacement and the total amplitude is 10 cm. Okay, 10 cm. This is the total amplitude, 10 cm. This is based on example 7.4. Okay, so the question asks you the velocity and the acceleration here, and also the net force here. Okay, so we got here negative, and here is also negative. That means this both quantity F net and the acceleration is always the direction of force, and acceleration is always opposite the direction of the displacement. So this is the direction of the displacement, downward direction, but the direction of F and A is upward. It's always opposite. Okay, that's why we got the negative sign here. So again, I repeat again that it is optional to you. If you want to put negative 0.05, the answer is still correct. Okay, so it's up to you. So the important thing, you understand what is meant by the negative sign here. Okay, that is example 7.4.